Throughout the 2020 International Astronautical Congress, we've heard about innovators with new ways to commercialize and discover new things in the final frontier. But before we strap one of these products to the top of a rocket and expose it to the extreme environment of outer space, we need to be sure that it will be able to survive and operate in these extreme conditions. One such condition is microgravity. In this presentation, the UWA Aerospace team will be discussing how we plan to meet this need through the creation of a low-cost open-source project that we call EMU. EMU is essentially a model rocket which we've turned upside down and attached a weather balloon to, taking it to an altitude of 30 kilometers. From here, we cut the connecting line and allow it to plummet towards the Earth. Due to its optimized design and low air resistance at this altitude, this will allow us to approach near microgravity conditions for up to a minute, allowing us to test out a range of different experiments. As soon as it approaches the thicker atmosphere, we deploy a number of parachutes, allowing it to safely return to Earth. Obviously, there's a lot of redundancy going on here, and the whole test is taking place in the Australian outback, just so we don't accidentally hit anyone. EMU costs around $200 per flight and can take a payload of up to a few kilograms. Most of these costs come from helium and the balloon material. Similar microgravity platforms, such as the German Microbe balloon drop facility, have been done in the past, but carry much heavier loads and can cost thousands of dollars per kilogram of payload. We foresee universities create their own EMU test platform, giving researchers and innovators low-cost access to a microgravity environment. Designing, building and testing the project is UWA Aerospace, a team of student engineers and scientists from the University of Western Australia. Since 2018, we've been building our own advanced aerospace projects to give us practical experience in engineering. We divided this project into simulation, aerostructure design, avionics and recovery.
By using simulation software such as ANSYS Fluent and SolidWorks Flow Simulation, we adjusted and validated our designs. Now, to keep things in perspective, our drop altitude of 30 kilometers places us well into the upper stratosphere, where air pressure is well below 1% of the pressure at sea level, and air temperature can go as low as negative 50 degrees Celsius. This extraordinarily thin atmosphere, however, works in our favor. It reduces the aerodynamic forces experienced by our experimental platform and lengthens the time in microgravity. The first step of simulation was to adjust our draft design of the inverted rocket. From past research papers, we knew that our von Karman style nose cone was optimal for our application. However, we knew that the rest of our fuselage could do with a bit of work. By optimizing the fin thickness, we were able to reduce flutter effects, and by carefully tapering the rear 1/3 of the rocket, we were able to reduce the recirculation zone and reduce our total drag force by an astonishing 15%. Then, by modeling the full fuselage of the inverted rocket, we were able to test the drag force exerted upon it at varying temperatures, pressures, and velocities. Our preliminary simulation results help us to prove that EMU will be a valid microgravity experimental platform.
All parts within EMU have been designed to be manufactured by us or bought as off-the-shelf components. As a result, all the materials are low cost and easily available in a university setting. Our composites are all hand-laid by us from scratch using fabric and resin, and where necessary, single-use molds are made from 3D printed PLA or on a lathe. Where higher precision parts are required, parts are laser cut or machined in a CNC. By making the entirety of the rocket ourselves, we've removed the need for expensive machining and production costs, making for a very cost-effective launch vehicle. The overall design of EMU is similar to that of a high-powered model rocket and is split into 3 sections. A fiberglass nose cone houses our custom electronics and is easily removable from the rest of the airframe. A machined aluminium tip protects against melting at supersonic speeds. This is followed by the payload section, which is a modular compartment for any scientific experiment or instrument. Long steel threaded rods span the entirety of the bay to transfer high parachute forces through the rocket and away from major components, whilst also allowing for modular fastening of payloads using metric hardware. Strong 3mm thick walls protect the contents inside from weather conditions or any turbulence experienced during landing. 2 removable payload panels allow for easy arming of electronics, as well as mounting to the walls of the airframe without damaging the reusable shell. The tail section is made from carbon fiber and houses our custom supersonic recovery mechanism and electronics. Fins provide aerodynamic stability of the rocket through freefall, ensuring that it doesn't spin uncontrollably so that all interior instruments are safe. Since the payload is located in the middle of the rocket, we're able to accommodate a range of masses, as the centre of mass position remains approximately constant. Since our materials are made by us, we've conducted materials testing to ensure that they're strong enough to sustain the forces during flight. We're confident in the ability of the launch vehicle to safely deliver the payload back to the ground.
To address the challenges associated with controlling and monitoring EMU's flight, we have developed our own custom avionics system which consists of 3 parts: the control unit, receiver, and battery pack. A custom design enables us to implement exactly the features we need for a fraction of the cost. The control unit features a microcontroller which takes inputs from sensors and determines when to deploy the parachutes. Deployment is confirmed when a corresponding shunt in the recovery bay is yanked out. The sensor suite includes both temperature and vapor sensors, a vacuum-capable barometer, and a 9 degree of freedom inertial measurement unit. It also logs data to a micro SD card and transmits GPS information to a ground station using the onboard transceiver. The control unit also operates a heating system in the battery pack to help prevent undervoltage conditions forming on the lithium-ion cells due to low temperatures. The battery pack itself is rechargeable to reduce cost per flight and contains our custom battery management system.
With this venture, recovery team has faced a new set of challenges. EMU must deploy a parachute at supersonic speeds and an air over 13 times less dense than sea level. After the free fall period, a small drogue parachute is deployed, with a larger main deploying 300 meters above the ground. It was decided that both parachutes should be deployed aft of the EMU platform, with the drogue parachute piloting the main out to prevent tangling. This is an off-the-shelf CO2 deploy mechanism known as the Peregrine, and we're using it to deploy our drogue parachute. The manufacturer tested its high altitude operation, and we confirmed its performance through a series of ground tests. It works by having a seal black powder charge push a CO2 canister into a sharp spike. This pierces the canister and allows the gas to vent into the adjacent drogue compartment, forcing the parachute out. Since the main is connected to the drogue, we needed to ensure that the main was not going to be prematurely pulled out by the drogue. We took inspiration from the three-ring mechanism used in recreational parachuting. It is a force reduction system that allows the separation of a section of cord in high tension without severing of the load-bearing section of the cord. We designed and sewed it ourselves, testing its load-bearing capacity with an Instron machine. Our current iteration takes a maximum load of over 6.8 kilonewtons. A nichrome wire cutter releases a chute. This works by passing a large current through a high resistivity nichrome wire, which heats up rapidly, allowing it to sever the release cord.
Before this project, UWA Aerospace had no experience with high-altitude balloons. So, in parallel with the technical design of the project, we worked closely with the Civil Aviation and Safety Authority to get us more experience with high-altitude ballooning. The UWA Future Farm, located a 2-hour drive from the city, were happy to let us use one of their fields as a launch pad. At our first attempt, we inflated the balloon and had it ready to go, but due to windy conditions on the day, the balloon hit the ground and popped before launch. We had a backup, but overinflation again left us with a burst balloon. Last month, we returned to the farm with a much better procedure, inflating the balloon inside of a shed. Finally, releasing our proto payload was incredible, only slightly tempered by losing radio connection shortly after launch. A backup phone showed that we were closely following the predicted route, but even the use of a drone couldn't help us find it in a field of canola. This summer, we'll be combining all of these lessons and designs into one final product. We'll then undergo successive tests where we start with mains deployment, drogue deployment with main deployment during flight, and finally a full drop test from 30 kilometers. We'll then send our first payload containing a range of accelerometers in order to obtain a more detailed flight profile. We hope to share these results in person at the next IAC before publishing our designs online and opening flight slots to local startups and researchers. The future of microgravity research has never been more accessible.